Welcome back. This is Math 2010, the linear algebra, and this is part 3 of linear independence and spanning sets. We'll continue our discussion on this lecture throughout the next few minutes. So what we are discussing next has to do with the ability of a set to be a spanning set. So we have already defined and illustrated cases for being for a set with elements, with members that are linearly independent. So we have already outlined what does it mean to be linearly independent in a vector space in general. But we are going to be interested in sets that have both properties, the property of linear independence together with the property of spanning, of being a spanning set. So if we consider an abstract space called a vector space, remember two operations, scalar multiplication and addition, together with the 10 properties that define a vector space, um, then we are going to consider a subset S of that vector space V, and we would like to address how to construct a subspace of this form, right? So remember that notation, this notation here, denotes the span, right? This is the span of um, the set S. In other words, all the members, all those elements in that set S are now considered in a way in which all possible linear combinations of those elements, all possible linear combinations of the members of S are considered over that all possible values of scalars in those linear combinations. Okay, so so reading this a vector space. Suppose in a vector space V, we suppose we're given a set of vectors S, and then we can immediately construct the span of S as a subspace using a definition pointed here, and then we can be assured by a theorem that that construction provides a subspace. So the span of a set is always a subspace of the vector space where the set resides on. So suppose now we're first given a subspace that is a subset of a vector space V, and can we find a set that is the span of which is exactly equal to the given subspace? Okay, so we're working with a given subspace W, and can we find a set that has a property that the span of that set is exactly equal to W, where W is, that's what we're assuming here. So in other words, can we find S such that the span of S equals W? And remember, we're assuming that W is a subspace of the vector space V. Okay, so this will be a little bit of a quest. Typically, that subspace is infinite. There is many members in that subspace, arbitrary subspace W, and we're searching for a finite set of vectors, of finite number of elements, okay, a finite number of elements of the vector space V that we can combine a linear combination and build all of W, okay? So yeah, let's see what we have next here. So here we have a definition, and that says to span a vector space, suppose V is a vector space and a subset of that vector space is a spanning set for the entire vector space if the span equals the vector space. Okay, so um, let's work out a few examples of this. So here we revisit this member of P4 this element, not element, but this um, subspace of the vector space of polynomials of degree 4 is defined by all those polynomials of degree 4 such that they have 2 as a root. They have one of the roots equals to the number 2. So that polynomial evaluated at 2 equals 0. This is a subspace of P4, and what we're going to consider now is a set S that contains the following elements. Okay, so it contains x minus 2, it contains x squared minus 4x plus 4, it contains this element, and then also this other element. In other words, we're thinking here of S as something that looks as U1, U2, U3, and U4. Okay, so even though W, um, that's the idea before. W may be a set that contains infinitely many. Um, we are now considering a set that contains only 4 elements. Okay, and we are going to do some calculations. So we can verify easily that each of those members U1, U2, U3, U4 is um, in W. So this verification here, this implies that U1 is in W, right? We evaluate x minus 2 at 2, and then that gives us a 0. So it's not difficult to verify that the second, right, the second member, this implies that U2 is in W. Then we have another expression which implies the U3 is in W, and so is the last one. So U4. All those U1, U2, U3, U4 are members of W. Okay, so we would say that each of those elements is a member of W, so therefore the entire set is a subset of W, and that's how we would write it. We would write as uh, this notation looks a little bit like less than or equal to, right? If these were numbers, we would say, I don't know, 3 less than or equal to 5, strictly less, but you know what I mean. So, but with sets, we use a notation that's kind of similar to the letter C, but that's the notation to say that S is a subset of W. So now, because W is closed under addition of scalar multiplication, W being a subspace of P4, then we have that this may or may not be entirely obvious, right? So if you consider any for any scalar alpha and any u in W, you have that alpha times u is also in W. This is one of the properties of vector spaces, right? So now consider something that looks like alpha k uk, okay? And then here this k goes um, from 1 to m, right? So then these over all possible values of k, then this is also in this is also in W, because each of these is a scalar multiple, and the sum of scalar multiples is also in W. So this is what this argument is about, is assuming that the span is also a subset of W. Now, what we would like to do is to show, so and previously we had established, maybe if I give you some hints here. So what we want, what do you want? What do we want? We want W equals to the span of S. Okay, so this is an equality in terms of sets. And so what we managed to do first is to show or to argue that the span of S is contained in W. The span of S is a subset of W. So what we will do next is to argue for this part. We're going to argue that W is also contained. So remember, if something is contained in W and also W and W is contained in the span. If the span of S is contained in W and W is contained in the span, then we conclude that W equals to the span of S. That's where we're heading. Okay, so to prove that W is contained in the span, we're gonna work with the following. So we're gonna choose an arbitrary member of W, and we're gonna write that as R of X. This is something that has 1, 2, 3, 4, 5 coefficients, right? So A here denoted A, B, C, D, and E. And because we're choosing an arbitrary element, remember, W, that polynomial degree 4 has a property that when evaluated at 2, that is equal to 0, right? So, but that also means that while evaluating at 2, then we're going to get an expression here that involves A, B, C, D, and E. Okay, and that expression looks like 16A plus 8B plus 4C plus 2D plus E. And that equals 0. So what we're going to do next is that we'd like to write R, this arbitrary element in W, as a linear combination of vectors, as a linear combination of those members in S, right? So here's R, and so in other words, we want to write this as alpha 1 U1 and then alpha 2 U2 and alpha 3 U3 plus alpha 4 U4, right? So remember that U1 here is x minus 2 and so on. So here's the scalar times U1, the scalar times U2, the scalar times U3, and then the last scalar times U4, okay? And this means that by what's happening here, well, we can fold, right? We can multiply x1 times alpha 1 times x, alpha 1 times 2, and do the same for every expression here. And then we can group the terms that have the fourth power, third power, second power, and so on. And that means that R of x is expressed in this way as being expressed as a linear combination of elements in W. So this leads to the following, because this is also the other way of interpreting that arbitrary element of W when evaluated at what happens if we evaluate this at 2. That means that we would have to evaluate each expression here, replace x by 2, so you have 2 to the 4th, 2 to the 3, and here you have 2 to the 2, here this becomes 2, and then there is no 2 over there. So 2 to the 4 is 16 alpha 4, this is 8, and so on. So this will lead to a set of equations that when compare, you know, as we handle equations in P4, then we find these variables here. I mean, these equations over here. So to finish our proof, what we have to do is to solve these equations. Don't be distracted with these A, B, C, D, and E. They are constants, but we need to find values for alpha 1, alpha 2, and alpha 3. So form an augmented matrix and row reduce. And this is what we'll be finding with the caveat that this last line here is exactly equal to 0 because of the way in which we're thinking of this problem, one of the assumptions we made. But this implies that it's possible to find values for alpha 1, alpha 2, alpha 3, and alpha 4, each of them equal to these constants. Okay, so this help us to conclude that indeed W equals to the span of S.